right? Last time in class, I made the argument that we didn't start calculus, even though we're halfway through, a little bit more than halfway through October, we did not start calculus yet, not until I introduced you to the equation for the instantaneous rate of change. And that's what we're going to basically be doing again. So the assignment that is due today is 3.1, and 3.1 is the derivative of a function. The derivative, let me zoom out a little bit, of a function. And the way that I explained this last time for what was that 2.6 is that, we have Isaac Newton who is struggling with this idea if we have some type of curve here, and I want to find the instantaneous rate of change somewhere on this curve. Well, we need to back up a little bit and consider finding the average rate of change and somehow connect it to the instantaneous rate of change. So if I have some secant line that goes through the curve like this, let me draw that a little bit differently. I have a secant line that goes, no, I don't want to draw it like that either. And the secant line goes through the curve at two specific points, right? I'll use a different color. How about green? At this point right here and this point here. Now we want to set this up generically, so this will solve for any point, for any 2 points. So we'll call this some value x with some corresponding y value of what? If this is my function, if the curve is my function f of x, then the y here is my f of x. So then we have some distance, some distance between, some x or horizontal distance between our two x values. We'll call this some value of h, which means then the x value for this corresponding point is what? Yeah, it's x plus h. It's x plus h. It's this value here of x plus another value here of h, with a corresponding y value then of f of x plus h, yeah. So if we use our equation for an average rate of change, where we have here's our slope for the average rate of change of the difference between our y values over the difference between our x values, then we would have, if we plug those corresponding values in, we would have something like this. We'd have the difference between our x values, that's going to be this, sorry, y values, that's the difference, our rise, right? So that's going to be f of x plus h minus f of x over the difference between our x values, and that would be our run. So that would be this distance here. So from x plus h minus x, which can be simplified to what? To just h, yeah. So is that too far back? Can you guys see that? Drew, you're good back there? Go. So that gives us f of x plus h minus f of x over h. And Isaac Newton thought, well, if I want the instantaneous rate of change at, say, this point right here, why can't I just use the same value twice to capture this, what's called a tangent line? And let's see if I can draw, I'll do a purple tangent like this. Well, the problem with that is if I take the difference between my y values over the difference between my x values, and they're the same, then I end up with 0 over 0, which is an indeterminate form. Now, from our exploration of this class so far with limits, we've discovered that there are certain well, in fact, this, whenever we have an indeterminate form, we need to consider some of the tools we have for limits. This is going to become our limit as h approaches 0. So I'm literally, if I zoom into the equation or the graph, and I'm starting with this secant line, the blue line. Now, as h, this distance here becomes infinitely small, so this point here gets closer and closer and closer and closer and closer to this point here of x comma f of x. To make a tangent line, we're literally finding the limit as this h value approaches 0. It can't be 0, because if it is 0, then we have the same point, and then we have 0 over 0. But if we look at what happens when the limit of h approaches 0, becomes super, super small, then we can capture that instantaneous rate of change at that point. And this is where calculus it comes into existence, when it is discovered. It does not exist until this formula is created. And then all calculus is based upon, well, it expands from this concept in itself. So most of the time, we know how to do this with a shortcut. And most of your calculus will be done by using shortcuts, but you are still accountable for understanding how to do this equation. So I do expect for your homework for 3.1 that you do this the long way. You can certainly check your work by using the power rule, but I really, really need you to understand how to do this, because this can appear on your AP test. In fact, you should expect it to show up on your calculus AP test. So let's go ahead and do an example. Let's say that we have, here's my example. I want to find the derivative of f of x equals x cubed minus 3x. Now, before we do this the long way, I want to make sure that we do remember the shortcut way as well, because this is, ultimately the majority of the calculus that we do in this class will be done using the shortcut. If I have some function of y equals a times x to the power of n, how do I find the derivative function of that? Using the power rule. A times n. Correct. That is our power rule. And so using the power rule, what is the derivative of x cubed minus 3x? Three x squared. So if I have 3x to the power of 1, and we follow this rule, yeah, it just gives me 3. So I get 3. All right, that is my derivative. So I'm using this notation of f prime of x. It's an apostrophe. So I have f apostrophe in parentheses x, which represents the derivative of f of x. Riley, do you remember what a derivative is? If most of this class is going to be about finding the derivative, we need to know what that even means. What is, if I'm talking about finding the derivative of this function, what am I really finding? What does that mean? Finding the derivative. Isa, do you remember what derivative means? If I find the derivative of some function, what I'm really finding, what does that mean? Finding the tangent. I'm finding the slope of the tangent at any x value, correct? So I would literally, if I wanted to know what the slope was when x is, I don't know, 5, I would just plug in 5 right there for x, and that would solve, it would tell me then what the slope is when x is 5. Yep. All right, so let's do this. So that's the shortcut, just using the power rule. Now let's use the limit rule. In fact, I would argue, I have not done my research, so I don't know for sure, but it is my guess that Isaac Newton never discovered this. That all of the calculus he ever did was using this. So it wasn't until later that mathematicians discovered the shortcut by seeing lots of patterns. So let's do the same thing. We're going to use our equation then. I don't know if I'm just way too close or if that's too small. I don't know. So how could I do this using our shortcut method? This is what I want you to do with the homework. I want you, certainly you can check your work using the shortcut, but I want you to be able to do this by using the original derivative function. So our equation is right here. It's the limit as h approaches 0 of f of x plus h. What does that mean? If my f of x is right here, x cubed minus 3x squared, what is f of x plus h? Let's say that again. Is it, so if I'm trying to find f of, say f of x equals, let's make it simple, let's just make it linear, like 3x minus 4, and I want to find f of 2, how do I do it? Yeah, I just plug that value of x into the equation. That gives me f of 2 equals 3 times 2 minus 4. And that would give us what, 6 minus 4, which would be 2. So f of 2 equals 2 in this case. Now, what if I wanted to find in the same example? What if I want to find f of x plus h? You don't need to know what h is. Yeah. Minus 4? Yes. Yeah, we're just taking this value here and plugging it in. Just like with the 2, when the 2 replaced the x, then we just plugged the 2 in for x. If the x is replaced with x plus h, then we take x plus h and substitute that instead. So I don't know who that was. Was it Josh or Emerson back there? I think that might have been the direction. I think your intention was that this was supposed to be x plus h cubed, I'm guessing. I just heard something different. So x plus h cubed minus what? Yep, correct. Now that took care, so we still have our limit here, the limit as h approaches 0. Now that took care of our f of x plus h, but we still need this minus f of x. So the minus f of x then is what? Minus. What goes in here? Yeah, our f of x is right here. It tells us. So we're going to write that down. We have x cubed minus 3x all over h. How do we simplify this? How do I factor this mess here? Christopher? There's two different ways we can I'm sorry, I don't know if I said factor, I meant distribute. Yeah. So we can either distribute all this. So I have x plus h times x plus h times x plus h, and then distribute here, here, and here, and here. And then whatever we have here, we need to distribute here, here, and here, and then distribute, let's see, there would be 3 of them here, right? So we'd have here, here, and here, and here, here, and here, and here. Yep. So it just becomes this whole mess, or we can use what's called binomial expansion. I don't care which way you do it. Both are correct. If you don't remember how to do binomial expansion, I would suggest that you do it this way, where we just write out the x plus h times x plus h times x plus h and then distribute. So I'm going to try to do this using binomial expansion. And if I use binomial expansion, I have to use this pyramid, this of Pascal's triangle. And the question is, what row am I going to use? What row would I use for this one? Which one, I'm sorry?
Well, it starts with 0, so the 3rd section.
Yeah, so this is going to be the one we use, the third row. If we start, this is our row 0. This is our row 1, our row 2, our row 3, our row 4. It actually aligns really nicely if you think of it, of the first row as row 0. So we're going to use, we'll use this one here. And so when I expand this, remember when we expand this, we're going to get a polynomial. And polynomials are always written with descending order of exponents. So when I expand this, I'm going to write x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0, so forth for each one of the terms. So I'm just expanding this piece right here. So that gives me x to the power of 0 times x to the power of 3 times h to the power of 0. There's some coefficient in front, plus what? X to the power of descending order 2 times h to the power of x is descend and h is ascend. So h is going to be to the power of what? 1 plus some coefficient x to the power of 1, h to the power of 2. When we count up the digits, the exponents, we should always get 3. We should always get 3 when we add up all of the exponents, because that is the degree of our function. All right, so let's look at the next one. What's the next one? X to the power of 0, h to the power of 3. What are my coefficients? Yeah, it's Pascal's triangle right here. 1, 3, 3, 1. That's just this one little piece right there. That little piece is going to expand to that. So that's going to put me in trouble, it looks like. I'm running out of room. I think maybe I'm just going to have to erase Pascal's triangle. I just can't see any other strategic way to do this. Okay, so I'll just erase this here. Now, if you're okay with it, I'm going to distribute this -3 right there to give me -3x minus 8, -3h. You all right with that? What about this over here? What about this piece? Don't I have to distribute the negative? Okay, so that's going to give me -x cubed plus 3x all over what? All over h. Yeah, we need to remember that this is really a limit as h approaches 0. Okay, now what? Okay, what terms can I combine?
Well, yeah, there's an x cubed.
Yeah, this is x cubed right here. Yeah, so those cancel out.
And there's
minus 3x and plus 3x.
Yeah, those cancel out. Nice. So what's left? Now we have the limit as h approaches 0 of what? 3x squared times h plus 3xh squared plus h cubed. Isn't that what this is? Just h cubed? Okay, h cubed minus 3h. Did I capture everything or did I miss something? Did I get it all? Right now what? What do we do from here? Emerson, any idea? If I plug in 0 right now, then we're multiplying by 0 here, multiplying by 0 here and here and here, and then here. Don't we get 0 over 0? So there has to be something else I can do at this point so that I don't get this indeterminate form. Yeah, I can factor out an h. You are correct. So that would give me the limit as h approaches 0 of h times 3x squared plus 3xh plus h squared minus 3 all over h. Now what? Yeah, h divided by h is 1. That's gone. And so now I have this limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 3. Now what? Yeah, we can just plug in the 0 for h. These go away, leaving me with 3x squared minus 3. Using the shortcut method, what did I get? It was the same? Okay, yeah, using the shortcut method up here, we got the same thing. Okay. What if I said, for, let's use black. For f of x equals x cubed minus 3x, where do we, or where do we have tangent lines of 0? For f of x equals x cubed minus 3x, where do we have tangent lines of 0? Where do I have a slope of 0? How would I do that? Don't I use my derivative function? I'm going to use f prime of x equals, what did we say it was? 3x squared minus 3. 3x squared minus 3. How does that help? I want slopes of 0. Where do I have for this cubic function? Where do I have a slope of 0? Drew, any ideas? If I want a slope of 0, doesn't this mean my instantaneous slope? Wouldn't I make this 0? Close. Don't I make that? Doesn't the derivative mean the instantaneous slope? The instantaneous rate of change? So I'm going to make that 0. So I have 0 equals 3x squared minus 3. Now what? Okay, add 3 to both sides. I have 3 equals 3x squared. Now what? Divide by 3. That gives me x squared equals 1. When we take the square root, we need to remember something special. What is it? Yeah, we need to remember plus or minus the square root of 1. The square root of 1 is what? What times itself gives us 1? What is it? 1, yeah. So I have x equals plus or minus 1. So I have 2 horizontal tangents. Specifically, this is how we would finding one of the ways that you find a maximum and a minimum is by finding those horizontal tangents when this is 0, when your derivative equals 0. So let's graph this and see how we did. So I'm going to go to Desmos. My equation is f of x equals x cubed minus 3x. And we can see that we have 2 horizontal tangents at x equals 1 and -1. Pretty cool. What do you think it means if I graph my derivative? What do you think it means if I graph my derivative? And I have y equals 3x squared minus 3. What do you think that blue means? What kind of relationship does this blue graph have to the red graph? What's happening at these x-intercepts? When y is 0. Aren't those the slopes for the red graph? Wasn't the slope at the red graph 0? What do you think it means right here where we have, I don't know, do we look between x equals -1 and x equals 1 for the blue graph? It's all below the x-axis, which means all of the y values are what? Negative. Let's look at the slope of the red graph. The slope of the red graph from -1 to 1 is what? It's negative, it goes down. Now I'm saying that all of the other points for this blue graph are above the x-axis, which means what about the red graph? All of the slopes are positive on the right side of x equals 1 and on the left side of x equals -1. Yeah, my slopes, you can see the slope is your rise over run. You can see that the slope is positive. We read a graph from left to right. It's going up, 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 and then we reach that maximum point and then it reverses directions. We have all negative slopes between -1 and 1. We're actually literally graphing with the blue graph. We're literally graphing all the infinite slopes for the red graph. That's sort of cool. In fact, that is something that you have to learn for this class. Eventually, you're going to be given an equation, given a graph, and you have to find what the derivative function would look like based upon that graph. It's sort of fun. It gets fun. This is just so new to you still that it might seem a little overwhelming. So I probably should not introduce that to you at this point. All right, let's do another one. I do want to talk about all the different kinds of notation that we have when it comes to a derivative. Now, if a derivative is that important, remember, calculus is a huge idea. In fact, when you take calculus in college, we have first semester calculus, second semester calculus, and third semester calculus. This 1 year in my class is equivalent to the first semester calculus class. The second semester calculus class, if you took the BC class, that would be first semester and second semester combined. And then the third semester, we don't even offer it here at Highland High School. You have to go someplace else, like say to the Salt Lake Community College to take that third semester calculus class. And then there's a bunch of other math classes that use calculus as a prerequisite skill, a prerequisite course to take those other classes. So calculus is a huge idea, and it's all based upon this idea of the derivative. So we need to know what a derivative is. What is a derivative? Yeah, we're just talking about the slope. We're talking about the instantaneous rate of change, right? Anywhere on the curve, we're talking about the instantaneous rate of change, or what Miguel said, the slope of the tangent line for any value of x. So if derivatives are so huge, it's probably not surprising to hear that there's different kinds of notation as well. So let's talk about right now the notation for a derivative. So one way we've already seen it, if I have a function f of x, then the derivative of f of x is written like this. We could say f prime of x. We could say f prime of x. Or we could say the derivative of f of x. Both are acceptable ways of referring to this notation of f prime of x. We also have, what if I have just y? If I have like y equals 3x minus plus 4. Any guesses what the derivative of this is, bless you? Any guesses what the derivative of this is? Yeah, it's just 3. Because it's 3 everywhere, right? This is a linear equation. And so we know that this is my slope right here. So the derivative function is 3. And the way that I would show the notation would be to just have y prime. That would be my the equation for the derivative of y. So let me just get rid of all that. So another way of writing the derivative function is simply to write y prime. Here's another way, dy dx. This is not read dy over dx. It is read dy dx. dy dx. That's how, dy dx. That's how you read it, just dy dx, not dy over dx. Why do you think that this dy dx would be used to denote a derivative? Does this look like anything we already know? Yeah, it's our slope equation, right? The difference between our y values over the difference between our x values. Yeah. So dy dx is just like our instantaneous rate of change equation of slope. Yep. So that's just read dy dx. And another one would be, you can even simplify it to d dx. That's an acceptable way of, in fact, I feel like I'm crowding it a little bit. Let me go back. I'll just move this over. Or I could even say something like this. I could even go, or I could even say something like this. D dx of f of x. D dx of f of x. That would also be an acceptable way to refer to a derivative. D dx of f of x. Now, which one's more common? Well, they're all common. And so that's something that we have to get used to. When I was learning Russian, I was a high school exchange student to what was then the Soviet Union. When I was learning Russian, I thought, wouldn't it be nice if, in the Russian language didn't have so many synonyms? Why can't they just decide, like you have two words, for example, in Russian, you have slozhno and trudno, and they mean the same thing. They both mean hard. Why do we have to use two words to describe the same thing? Now, as a foreigner, I have to learn two words that mean the same thing. So why can't the Russian people just settle on one word to mean both? Well, they're not going to do it. We have lots of synonyms in English. Do you know why we have so many synonyms in English? Well, there's probably lots of reasons. Poets would like to have lots of different words that mean the same thing. It's also sometimes some words mean the same thing, but one is more, has, like connotations attached to it that might give it a deeper meaning of the same thing. You have language or English language did not originate in the same spot on Earth. It originated in many different locations throughout the British Isles, right? And so so the origin of these languages, and then when they're combined, end up you end up getting multiple words. In fact, my understanding, I've not done the research, but I suspect it is true. It's interesting that we have words like beef and cow that refer to whether the cow is alive or dead, which is sort of weird. But my understanding, and I could be wrong because this is what I've heard, not what I've researched, is that the word beef is from Scandinavia, from the Vikings, and cow is more of an English word. And then when the Vikings, with all their conquests and stuff, that word beef ended up working its way into English. And instead of just referring to the same thing as a living animal, they ended up deciding that the two would refer to whether the cow is alive or not. I think that's sort of interesting. In Spanish, you have two words that mean whether a fish is alive or dead: pez or pescado. In English, we don't. It's a fish. A fish is alive or dead, right? It doesn't matter. So, any questions about the notation? Which one's the most important? Which of these is the most important? They're all important. You have to learn all of them. And I'll try to use these interchangeably throughout this class so you get used to it. So let's look at, I'm going to go to Desmos. I'm going to clear this out. I just really, at this point, I just want to capture the grid. So we're just going to practice answering some questions with some of our new notation. Can you guys see that okay? Would it be helpful if I zoomed in? Or can you see it okay here? Drew, how do you feel? Is it, can you see back there? Okay. So what am I asking here? What is this? Well, we can't answer it if we don't understand what's being asked. What is being asked here? Yeah, I want to know what the slope is when x is 0. Unlike the notation, what does this mean if I just write something like this? Yeah, I want to know what the y is. What is y when x equals 0? That's what I'm asking here. Over here, I'm asking what is the slope when x is 0? You guys see the difference? So what is the slope when x is 0? Would it help if I zoomed in? What is the slope when x is 0? Yeah, it's 1/2. How do you calculate slope? Yeah, rise over run. Yeah. Well, you're absolutely correct. So from this point here, if I'm trying to figure out what the slope is right here, well, anywhere on this line here, my slope is a rise of 1 and a run of 2. So I have a slope of 1/2. Eleanor, are you good with that? When x is 0, our slope is 1/2. So my answer is 1/2. What about when, I'll zoom in again, maybe, I think this is more helpful to see it this way. What about when, what is this asking? Louder? Yeah, what is the slope when x is 2? Is it 1? It's not 1. Is it -1? Seems like it would be -1 because at this point right here, you have a slope here of a rise of 1 and a run of 1, but you're going, when you read from left to right, you're going down. So it seems like that's this piece here, my slope is -1. But isn't that at the end of this line here, which is a slope of what? 1/2. Do you see how we have conflicting information? We have conflicting information. Is this at this point right here, is the slope 1/2 or is it -1? So there's certain points where a graph is not differentiable. Differentiable means cannot take the derivative at that point. So in fact, this is sort of important. We'll have to come back to this later. I really want to define where a function is not differentiable. Let's just go out a little bit. We're going to come back to this in just a moment. I want to define when a graph is not differentiable. At what points? At what points is a graph not differentiable? What does differentiable mean? It means you can't take the derivative. We consider y equals 1/x. let's just use the power rule. Let's use the power rule and figure out what the derivative function is. If I graph this, it's going to look something like this. And if I take the derivative of this, well, y equals 1 over x is the same thing as x to the power of -1. So if I use the power rule, what do I get? -1. Don't we have to, for our power rule, don't we have to subtract 1 from the exponent?
Oh, yeah.
Yeah, all right, so let's go back over here. So that's going to give me x to the power of what? -2. We'll move it back down. So I have y prime equals -1 over x squared. Is that the same as this? Okay. Looking at this graph, for what value can x not be? X cannot be 0. X cannot be 0, which means that x is not differentiable when x equals 0. The function is not differentiable when x equals 0. Let's look at the graph. Does it make sense looking at the graph that there is no slope when x equals 0? Yeah, in fact, yeah, there's no slope there at all. Is the slope, well, I guess it would both be negative up here, but there's no point there. There's no x value there to find a slope of. So there's certain points where a graph is not differentiable. Riley, what does differentiable mean?
Not there. So the tangent's not.
Yeah, there's no tangent. There's no, well, there could be a tangent, but it's not, there's no slope. There's no slope at that point. So let's go back a little bit further. Oops. So at what points is a graph not differentiable? One is called a corner. Well, a corner. A corner is where the graph looks like this. This is my corner. That's sort of the problem we have up here. Why is this graph not differentiable when x is 2? Yeah, we have two different slopes. We have a positive 1/2 if we go from the left-hand side, and we have a -1 if we go from the right-hand side. So we have conflicting slopes. So we would say then that a corner is not differentiable. We also call what is called a cusp not differentiable. A cusp. And a cusp is very similar to a corner. In fact, I almost think that they should be called the same thing, because the reason for a cusp and a corner to not be differentiable are the same for the same reason. When you approach from the left or the right hand side, you end up with a different slope at that point. And I think something like, if I have y equals the absolute value of x, right? Let's do some type of transformation. Where is this graph not differentiable? Yeah, right here at 3, it's not differentiable because we don't know whether that point has a negative slope or a positive slope. Yep. Now, here's another one. Y equals x to the power of, I don't know, 5 halves? No, 5/3? No, I don't know. 5/4? 5, how about 3? What do you think the slope is at this point? Any guesses what the slope is at this point?
Zero.
If I drew a tangent line, what does that tangent line look like? It's a vertical tangent line. What's the slope of a vertical line? Is it zero? Isn't, so I would say that this line here has a slope of zero, because if I had a marble, what direction would the marble roll? It wouldn't, because there's no slope. What about a vertical line? What's my slope? Is it still zero? Does the marble just stay there? It just drops. So what's the slope of a vertical line? It's or undefined. We say it's undefined. Is it infinity? Maybe. I would say that the way mathematicians just say that it's undefined. We just say it's undefined. So we're going to say that third one is going to be a vertical tangent. If you ever get a vertical tangent, it cannot be differentiable at that point. I have something like this. This is my vertical tangent right there. The graph is not differentiable at that point. Let's see if that's true. What was my graph that I had? Go ahead. Can you guys see what that is? I don't know if you can see what that is. Control plus. Oops, I went too close, I think. Control minus. When I have a vertical tangent at that point, what's my equation? X to the power of 3/5. X to the power of 3/5. Let's see algebraically, if I have y equals x to the power of 3/5, how would I use the power rule for this one? What's the rule for the power rule? Do you guys remember the power rule? What's the power rule? A times n times x to the power of. Okay, let's use the power rule. Times x to the power of. -2/5, yeah. And because it's negative, we'll move it to the denominator. So I have y prime equals 3/5 times x to the power of 2/5. What value of x is not allowed here? What value of x is not allowed for this derivative function? X can't be what? 0. Yeah, x can't be 0, because if it's 0, I have 0 in the denominator. So for this graph, let's go back to my graph here. Yeah, right here it shows that for this vertical tangent at this point right here, I do not, it's not differentiable when x is 0. Okay, so we found 3 at a corner, at a cusp, at a vertical tangent line. There's one other reason a point cannot be differentiable. Any guesses? If it's a vertical asymptote. If it's a vertical asymptote, isn't that one of our 4 ways that a graph is not continuous? Is discontinuous? All right, so let's talk about the points of discontinuity. So the points of discontinuity, there's 4 different types of points of discontinuity. One looks like, so points of, I'll just write it down here. Points of discontinuity. Good, not continuity. I don't know how to spell it. I'm spelling it wrong probably. Points of discontinuity. All right, one of them is your infinite discontinuity, right? What was another one? Yeah, we have a removable. So it looks something like this is removable. What's another one? Sorry? Yeah, jump. Sorry, you have a deaf teacher. So you have a graph going around over here. It stops and then continues over here. This would be a jump discontinuity. There's a fourth one. An oscillating. We also have an oscillating discontinuity. Oscillating. So when the graph, this is some type of periodic function, and the graph just starts oscillating like crazy, and we have no idea what's going on in there. We don't know whether, how is it continuous? Am I here or here at some particular point? I don't know where we are. So an oscillating discontinuity. There could be some interruption there, but at the same time, because of all of this oscillation, I can't really see what's happening there. Do you think I can find a slope at any of these points of discontinuity? Do I have a slope here at x equals 0? No. Would I have a slope when x equals whatever point the x is missing? Do you have a slope when a point doesn't exist? No. What about if we have, I don't know, maybe something more obvious like, what if instead we go the opposite direction, right? So the graph looks like this. Do I have a slope at whatever x value this is? No. Do I have a slope in here somewhere? No. So my fourth reason for not being able to find the fourth point that is not differentiable is what? Points that are what? Discontinuous. Yep. So any discontinuous point. Okay. Ellie, what are the 4 points that are not differentiable? Perfect. Yep, a corner, a cusp, a vertical tangent, and any point of discontinuity. You are absolutely correct. Emerson, what are the 4 points of discontinuity? Yep, infinite, removable, jump, and oscillating. You are absolutely correct. Nice. Let's go back up to, are you guys still copying this? You good? Okay. Kata, it's good to see your pooch back. Your doggy is always welcome. All right, so let's look at this one. So what's the answer to this one then? When x is 2, what's my slope? Louder? Yeah, we just say, does not exist. It doesn't exist. There is no slope there. All right, what about 3? What about when x is 3? It also does not exist for the same purpose. Which of the 4 points of discontinuity, or sorry, let me start over. Which of the 4 points that are not differentiable is this one? Yeah, it's a corner. Yep, it's a corner. So we say does not exist. What about 4? What is the derivative of our function when x equals 4? Let's zoom in so you can see. Yeah, it's 1. Yeah, at this point right here, we see that we have a slope of a rise of 2 and a run of 2, and 2 up, 2 over can be simplified to 1 up, 1 over. And we just get 1. All right, so I'm going to zoom out. So the answer for this one is 1. Let's write that a little bit better. What about 5 when x is 5?
Is it also 1 since we also accept 0 at the end?
Can you have a slope at the very edge of a function? Yeah, you can. And so the answer is 1. Yep. Both of these are 1. Any questions? Emerson, are you good? Okay. All right, so here you could be given a question. I actually have seen questions like this on past AP tests, where you have to describe what this means. I have the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. What the heck does that mean? Yeah, this is the same thing. This means the same thing. Oops, that's not what I meant. This is the same thing as f prime of 2. Do you see it? So I literally mean the slope. This is the slope when of my f of x function when x is 2. So this is the slope of the f of x function when x equals 2. Do you want me to explain that more, or do you guys feel like you understand it? Riley, do you need me to explain that? You're good? Okay, let's do another one then. What if I'm given this? So what does this mean? Yes? Do you want me to write it better? What does it mean? Andrew, any ideas? Okay, do you know what my function is? It means the same thing as this, but there's some specific stuff in there. Means the same as this, but I know this time what f of x is. So this is the slope of f of x, but what is f of x? Yeah, this is our function of sine of x. So this is the slope of our function y equals sine of x at what point of what value for x? When what? Yeah, when x equals pi over 4. Yep. Well, how did I get this mess over here? How does that make sense? So if my function is, so if my limit function is the limit as h approaches 0 of f of x plus h minus, that's messy, h minus f of x over h, then, and my function is sine of x, then I replace the x with x plus h to get this. Does everybody see that? One more time. If my function is sine of x, then I'm going to plug my x plus h into it to get this value here, correct? Assuming that x is also pi force. And then I'm going to take this value here. That is my f of x. So that goes here, which is here. But x is what? It's pi fourths. So what is sine of pi fourths? If these are the same and my x is pi fourths, because that's what we said it was, then what is sine of pi fourths? Use your hand trick. What do we get? What? What do we get? What finger do we put down? Which is my pi fourths finger? It's the middle finger. Sine is from the pinky direction. How many fingers from the pinky direction? 2. What's the formula in the palm of our hand? It's the square root of x over 2. What is x? We have 2 fingers. So this is the square root of 2 over 2, isn't it? Isn't that the same thing as this? If I have 1 over the square root of 2, square root in the denominator is not considered simplified. So I have to rationalize the denominator. How do I rationalize the denominator? We multiply by 1 in the form of what? Square root of 2 over the square root of 2. The numerator is the square root of 2. What's the denominator? What's the square root of 2 times the square root of 2? It's just 2. We get the same thing. So this is our sine of pi fourths. Are you good with that? Okay. So we do need to know that. When we see this notation, I've seen this on AP tests. They say, what is this? What does it mean? And that's the answer. This is the slope of our function of sine of x when x is pi fourths. That's what it literally means. Okay. Get rid of all that. I know we don't have a lot more time. but we do have some time. What if I want to find f prime of x for f of x equals 1 over x. We know what this is already. We did it earlier today. We did this using the power rule. How do we do this using the power rule? This is the same thing as x to the power of -1. Using the power rule, what do we get? F prime of x equals what? Negative x to -2, which is the same thing as negative 1 over x squared. Does that look right to you? Using the power rule, that's what we get. Can we do this using our other method, our limit? So my limit, let's use a different color. Is everybody good with the power rule? The power rule may need to be one of your flashcards. We will be using the power rule the entire year. You need to know the power rule. You need to know the power rule. Do you want me to review the power rule again? You have to know the power rule. Okay, now this other idea of the limit as h approaches 0 of f of x plus h minus f of x over h is not something we're going to use very much. We are going to use the shortcut for most of this class. But you are expected to remember how to do this for your AP test. So what's my f? If f of x is 1 over x, then what is f of x plus h? Isn't that just 1 over x plus h? Minus f of x, which is 1 over x. All over h. Oh, not equals. How do we solve for that? Oh, that's why Mr. Hall wanted us to learn how to solve or simplify complex fractions. So how do I add fractions? Yeah, so we need to multiply over here by 1 in the form of x plus h over x plus h. And we need to multiply by 1 in the form over here of x over x. I know we don't have, I'm going through this really fast because we're running out of time. So that gives me x over x times x plus h. And then we're going to just add it. So minus x minus h, does that look right to you? If I distribute this negative. Okay, now what?
Well, we factor the bottom and we account for the x in memory.
Yeah, these cancel out right here. X minus x is just 0. That's gone. And so I'm left with the limit as h approaches 0 of negative h over x times x plus h. Which makes me a little bit nervous here. We should have been able to factor out an h, and I don't see that that happened. X. X. Ah, yeah, we forgot all this down here. No, over h. Okay, yeah, thank you. Was that Miguel? Miguel, look at your brilliance. Miguel says, I did all of this here and I moved it down to here, but what happened to the h? Thank you. Because I was thinking at this point, if I plug in a 0, it's allowed, and then nothing, it all becomes 0, which doesn't make sense. So this is all over H, which means this is all over H, or H over 1. When you divide by fractions, here's a tip. Is everybody good with how I got to this point? Okay, if I do keep change flip, so I have the limit as H approaches 0 of negative H over X times X plus H times 1 over H. Now what? Cancel the H's, correct. Let's cancel the H's. This oops, what happened to that H? That goes away. And that leaves me with the limit as H approaches 0 of negative 1 over X times X plus H. Now what? Now we plug in 0. Do we get the same answer as this? If I plug in 0, X plus 0 is X. X times X is X squared. We have the same thing.